Unit 3. Kind of to preface what's going on, because the more you can like connect everything, right, the better the brain does. The more neurons that can fire and make bridges, it just makes your learning that much stronger. So try to connect things that are going on here. Now, first off, what I do want you to recognize is this unit is weighted heavier than other units on the AP final test. They say, so unit 1, they say is weighted 7 to 9%. So 7 to 9% of the AP test will be from unit 1. 7 to 9% will be from unit 2. It's 12 to 15% is unit 3. So there's 2 units that are weighted heavier, unit 3 and unit 8. So they're definitely ones where, not to say like you ignore other units, but like this one you really want to make sure you have a firm understanding on, because it's guaranteed a big chunk is going to be what this is about, okay? Now, what this unit is in terms of like the theme, or what the title of it is it's all about solids, liquids, and gases, which sounds like quite simple, right? And it really is if we keep it that way. So what we're going to be looking at with these 3 phases of matter is what's going on with our eyes. So how do they behave in what we see? How does that connect to the molecular view? Okay, so that's what we're going to be doing a lot of today, is diving down into the molecular view and then connecting it to, symbolically, how do we write it? How do we calculate these values, the mathematical side of it as well. Okay, but as we go through our different phases, so today we'll talk primarily about solids and liquids. Next time we'll continue with liquids, and then we'll get into gases after that. But really make sure that you're connecting all 3 sides of that triangle, right? What are you seeing? What's going on that causes it? Okay, a big thing I'm going to say a lot these next 2 days is that structure determines function. This is a fundamental cross-cutting concept across all sciences, that the structure of things determine how they function. We've already seen this already, right, as we talked about metallic and ionics, that the reason they behave certain ways are because of the way they're built at that small level, okay? So to get us started and to give you, I need to pass these back for some of you, but to give you some smiley faces to start off, go to that first top of your notes, and there's 3 boxes there, okay? I want you to work with your table buddy and draw 3 pictures for me that show a relative model at the molecular level of what water does as a solid, a liquid, and a gas. Okay? And you can draw your water like little Mickey Mouses, or you could draw it as just little bouncy balls. That's fine too.
So we're going to draw the circles big, so we have to draw less of them. Well, they touch. They're very touchy. Oh no, those ones are touchy. The water molecules touch each other?
I knew what the touch was, but I don't. There's an IMF acronym in one of these.
Star Wars what? Oh, I know what a YouTube is,
yeah. Oh my gosh, I never even made that connection. That's funny. Now we gotta find a way to connect it to that.
That's a solid. That's a solid. Alright, so for liquid, you just sort of... They're vibrating.
Water's like the dairy.
They got some vibrations.
I don't tell you right away, but think about it, and I think you'll figure it out right away.
Oh yeah, look at that. Look at them hanging out there. Yeah,
all right.
So that's,
now these don't have to be perfect. Those of you that are like trying to be Michelangelo of water, okay, just draw some pictures. It's fine.
They're zooming. Oh my gosh, you know what I should have done? I should have drawn like solid. Amy isn't talking. Amy's actually
The soccer team are playing in the semifinals right now.
And they're winning 1-0.
What?
They're winning 1-0.
No, it's tied now. I'm not live streaming it.
No.
I know.
It's alright, I can't believe they beat Lone Peak.
No, they didn't.
Well,
Lone Peak just,
Syracuse.
oh, Syracuse.
Alright, so that's our
I
icebreaker.
know. But it's okay. There's still 20 minutes left.
Looks kind of like this.
I didn't. Were they
Okay,
broken?
and
was
then
like,
gas
it was
is just
wasn't
sort
quite
of.
all the way from midfield, but it was like almost from midfield, and she curved it, and it went in because like the goalie was like ready for it, but then one of the Lone Peak defenders like kind of like jumped up and kicked her foot out.
It went off her.
It went off her.
So it was
and
actually
the
an
goalie
own
was
goal.
Kind of,
Oh,
yeah.
wow. That's crazy.
Yeah.
Okay. If you have, now there's various representations, but we're just looking for the main idea here, okay? So in your solid picture, if you have shown something about that the movement is very little, the molecules are close-ish together, then you can have smiley face. And they're kind of like maybe stuck in a certain orientation because they don't move. Okay, it's kind of more organized looking.
Can we get extra points if it's a swan sculpture ice?
No, but Alex will give you a high five. Maybe. Okay, yeah.
She controls us.
Yeah, Alex. No, I gave you that.
Technically you don't have that yet, but that's the thing that you do. Because we'll get there. But if you don't have that yet, that's okay. Okay, in the water picture, in comparison, you should have more movement. Okay? They should be less organized in a structured, like, stuck way. Maybe more spread out in certain parts. Okay, is what you should have in the liquid picture. And then in the gas, you should have them very far apart from each other. Okay? So if you have that, you can have 3 smiley faces total. Okay? Yes. Okay, with this idea, everybody, okay, give me your attention this way. Close your mouths. Okay, so this idea of solids, liquid, and gases shouldn't be anything new. Right, like my sister who teaches elementary school, like she teaches her 5th graders about the difference between solid, liquids, and gases and how they behave. But something that I don't think we really appreciate is how amazing this picture is. Okay, when we take what we see and take it down to the molecular level, what is the difference at the molecular level between water and ice?
One's a
Just the
crystalline.
way they're positioned. That's it. Same thing between a liquid and a gas. What's the difference?
Gases are spread out.
They're spread out. Like at the molecular level, if we were molecules, like right now, we'd be like probably solid. But then if we just all ran away from each other, we turned into a liquid. And then we kept running, we turned into a gas. Like that's the only difference between them, which is crazy because it's such a simple thing, but at our view, they appear and behave very different from each other, right? Like ice and water look different. They behave in different ways to some extent, but it's all about just that distance of the molecules, okay? So with that being said, there's a question right below those boxes I want you to answer with your table buddy, and I want you to have a discussion before you answer it, okay? The question says something along the lines of why then does water exist as a liquid at room temperature, but carbon dioxide is a gas? So get to the molecular view. What must be going on there if one is a gas and one is a liquid? Okay, discuss with your neighbors and write an answer. Go.
Yeah, because water has like stronger bonds, and so it's like it requires more energy.
Get your smiley face. You have to have something written on your paper.
Okay. Water has stronger intermolecular bonds. Or intermolecular forces. Use that word. It's like the cool word that everyone stay together. Carbon dioxide Because carbon dioxide is like da 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 da, but the water is like da da da, and so it's got the but this one it doesn't have that. It's warm.
But it's not that soft.
So
It's
then
feeding to the molecules.
it's and so then it sticks. It's sticky. It's sticky.
Maybe. That's a valid claim. Because if it was moving faster, they'd be farther. I'm not sure if it's right or not, but it is valid.
It's sticky.
It's a valid thought. Valid thought.
Yeah. The water is sticky. Yeah. Because water is polar.
Okay, answered in the next 30 seconds. You gotta have words on your paper if you want to smile face.
Like cause it be stay together. It's like ionization energy, but not. Yeah.
Okay, let's put this away unless you want to veto your corrections ability.
The sticky water is stronger.
Okay,
The
let's
more
think about this,
carbon
everybody.
dioxide.
And thank you for those that gave, like, when we do these discussion questions, it's so much more, that's not the right word I want to say, but it's more important for you to just discuss, even if your answer is wrong. Because you learn so much more from making mistakes than just not doing anything at all. Okay, so don't be afraid. We all have stupid moments together. Okay, once again, remember that when we have stupid moments, we remember them way longer than anyone else does, even though we're worried about other people. Okay, nobody will remember, and if they do, they need to get a better life. That's the worst thing to remember. Okay, so try to put aside the pride and just throw things out there. Don't be afraid to just be like, well, maybe this. If it's wrong, it's fine, but I promise you'll learn so much more if you say something than if you just are afraid to say something that's wrong. Okay? Now, with this idea once again, okay? Watch this. This is amazing. Okay, so if I'm a water molecule and sand's a water molecule, right? We talked about that the only difference is just the distance, right? So like now we're ice, now we're water, and now I'm a gas. Okay, right? So we said that water at room temperature exists naturally as a liquid, while carbon dioxide exists naturally as a gas. So we know molecularly the only difference between that is distance, right? The CO2 are more apart than the water. So what we're going to be learning about today, and kind of a lot of this unit, is what I have nicknamed the friendship forces. That there are forces that exist between molecules, okay, that signify whether they want to hang out together or not. Carbon dioxide, very little friendship force, right? It's just spread away from each other. Water has a much stronger friendship force, so the molecules are more prone to staying together. Now, temperature can influence the friendships, right? Because temperature, for those that haven't ever defined temperature, temperature in chemistry is movement of molecules. It's how fast or how slow they're moving. Okay, the higher the temperature, the faster they move. The slower the temperature, the slower they move. Okay, so yes, if you slow the friends down, it tends to bring them together and they're more prone to hang out. But some things you have to slow down a lot to eventually get them because there's just really no attraction between them. Okay, so these things that we're going to be talking about today officially are known as intermolecular forces, IMFs. Okay, so that's what this stands for. Keep in mind, though, that that force that we're talking about is the force between two molecules. So everyone take your little water friend, take him back if someone stole him from you. Put him back in its normal orientation for those of you that are breaking my water.
My water
That was funny. Okay.
Have a smiley face for that.
So with your water molecule, right? Why am I just holding it? Pretend.
Oh, that's
Okay. So the force we're referring to is not the force within. We will talk about those again, but that's what we covered last unit of an actual, this is a covalent bond. This force, and it can be done and you don't technically break it because they're designed to be that way, right? That is the covalent force within the molecule. The friendship force is the force that is felt between two separate water molecules. So if you haven't yet, make friends with your neighbor's water molecule.
No. I think they'd get one.
You didn't get one? I think doesn't have one.
Yay!
Okay? So, this right here, everybody.
Wait.
Okay? So what we're talking about here, an intermolecular force, everybody.
A water molecule is stuck to your chair.
Oh! You're making a mess.
Water molecule.
Okay, so this is the force we're talking about. And you can feel it, right? I mean, because there's magnets inside, but that's the point.
That's not.
They're particular.
No, hydrogen bonds are anytime hydrogen is bonded to something. Because hydrogen is so tiny that it gets way more cold than like other things. So like
Holy gold.
yeah.
It was
So
1-1, but
hydrogen
a
bonds
second
are
ago.
just when the hydrogen is bonded to something. So like in this case, it's bonded to the oxygen, and the oxygen is so much bigger, like itty bitty hydrogen, that it makes it way more polar than other molecules.
Now, the first part here, everybody, we're going to go through a little quick, because it's kind of just reviewing what we learned last term, but it does connect to it. So we're going to go through solids again, of ionic, covalent, and metallic, and matching their structure and their function. Okay, so let's start with, so first off, just a few definition words. So when something is a solid, we know that it is packed tightly, there's very little movement. They do still move. If you weren't aware of that, molecules don't ever stop moving under normal conditions. But often in solids, we consider it more of a vibrational movement than a translational movement. So they're not moving back and forth, but the bonds themselves can vibrate. Okay, solids can pack in a crystalline form or in an amorphous form. So sometimes it's very organized, sometimes it's not so much. And we'll see as we get deeper into the molecular view of why that is. Okay, so let's start with metallic bonding and review really quick the properties we saw with metals, because this is what they look like. Okay, so raise your hand if you remember one of our metal properties that metals always have. Good, so metals have high melting points. Why is that, Allison? High point, what the? Right, we got lots of positive and negative forces holding this together, and to melt it would mean you're trying to pull them apart from each other, right? So that electron C kind of binds it really tight. Good, have a smiley face for that. Aiden.
They conduct electricity while solid.
Good, so they are great conductors. Why is that, based on their structure?
Because it's like a sea of electrons, so if there's extra electrons, they can just float really easily.
Yeah, electricity just wave surfs, right? Across the top of it. Grant,
It's really malleable
why?
because I guess they like don't really care where they are because it's like free flowing, so it doesn't really
Right, like these ones are fine, like you can move the red ones this way and that way, but because the electrons are everywhere, they all still have what they're wanting. So, Rachel.
It doesn't dissolve in water,
Good, why not?
because the sea of electrons kind of prevents it from being really polar, so it's not polar.
Yeah, water can't pull it apart, right? It's held within itself too much, so. Yeah, good point. Have a smiley face for that. These are our main ones. Okay, all right, let's go to ionics. Okay, so same thing, just to review, so this is what ionics look like, positive, negative crystals, right, all stuck together. Happens because the electrons are transferred from a metal to a non-metal. Okay, some other people share some properties for us. Sam.
It's like, it breaks because they,
So why are they brittle?
because when it gets hit, the same charges line up and they,
Perfect. Yeah, and then they push apart, right? Because once it can shift if you apply enough force, but then they don't like who they're next to, and so they push each other apart. So, good, Sam. Sophia.
It also has a high melting point
Good. Why?
because there's just so many molecules and they're all just packed in there.
I mean, each one of these, like the purple is a true positive, the green is a true negative, and like think of like it's in 3D space, like it's really tight being held on there, right? So in order to get them to move, you have to put a lot of energy into it. So, very good. How does my face that? Other properties of ionics.
It's not conductive as a solid
Good. So why not?
because the electrons can't really move around.
Yeah, in solid form, right? The electrons have already transferred and now they're just stuck together. So, not solid conductive. How's my face for that? Trev?
It is conductive in water.
Good. So we have aqueous conductivity. And why is that?
Because the water can pull it apart and kind of weaken it because it's got structured electrons.
Yeah. So it pulls it apart so your positive and negatives aren't together anymore, and that allows a flow of a current to go through.
Trevor already kind of said this, but it's soluble.
Yeah, we'll add that on there, but definitely linked, right? Yeah, because in order for it to do this, it has to be soluble. But awesome. Questions? Hopefully that's kind of bringing things back after fall break of ionics. Okay, covalence. Now, we are going to talk about actually two different classifications of covalence in this unit. Last unit we just said covalence. The covalence we referred to last time and we did in the lab were known as molecular covalent substances. So this is the one you'll be familiar with our properties. Okay, with a molecular covalent substance, I don't know if you can tell the best from your black and white picture, but what this is showing is very similar to your water, but these are carbon dioxides. So it's showing a bunch of these, it's CO2, but all together, okay? So a molecular covalent substance is held together by intermolecular forces between the two different substances, or the two different ones. Once again, this is where we get into our friendship forces. What force does this CO2 feel in relation to the other CO2? Okay, so let's review what were some of our properties that we saw for covalence.
Low melting point.
Good, so these ones typically have low melting points. And why would that be?
Because they aren't like held together as tightly as the other ones.
And what are we breaking when we melt a molecular solid?
The friendship.
The friendship force, right? We're just breaking this. We're not ripping their arm off. Okay? And the other substances, like you're breaking the actual bond. In covalence, when it melts or boils, you're just moving the friends apart. Which, yeah, they may not want to and they may resist it. But it's not the same as actually breaking a true bond. Right? This can be done, like you can break the actual bond of water, but you have to send electricity through the water to do it. Like you need an immense amount of energy to actually break the bond itself. How's my face for that?
So are the friendship forces like ionic? It's like they're
Ooh, great point. It's not ionic, but it's like it in that it is a positive and negative force. But it's not the same as ionic in that ionic is an actual, the electron gets transferred over, and then this one is truly positive and this one's truly negative. But it is a Coulombic relationship again, which we'll see that word come up. So, good connection, Allison. Okay, what were some other properties of covalence we saw in the lab? Remember?
Is it just not conductive as a solid at all?
Yep, so these ones are not solid conductive. Good, have a smiley face for that. And why would that be, Harry?
Well,
Not in the outside.
the electrons aren't really moving for
Yeah, because they're shared in that one little spot, but there's not like that flow, right?
Yeah.
Yeah, good point.
What
Sam?
about water? Isn't water covalent and it's conductive?
Ooh. So, we'll get more into this, but water itself is actually not conductive. It's things that get put into water that make it conductive. So if you have pure, if it's just distilled water, it won't conduct electricity. But great, like, common misconception, right? Because we like, but when they say to not be in the swimming pool because water's conductive, technically it's the chlorine and the salts in the water that make it
So
conductive.
if you were to like
electrical, if you were to pour distilled water in an electrical outlet, is that not the same thing as?
Technically, yeah, it would be, I mean, once again, you have to make sure it's very distilled, right, which
And
is
it doesn't pick up
at the molecular hard to do. But yes, theoretically, if you were in a pool of water and it got struck by lightning and it was distilled water, you would be fine. But don't try that at home. But yeah, no. Okay, other properties of covalence we saw? Good, yeah, so they're not really, well, they were sometimes. So sometimes they're valuable.
Yeah.
What we'll see with covalence, everybody, is that most covalent molecular substances actually naturally already exist as liquids or gases because it's a friendship force bringing them together, not a true bond like ionics are. But sometimes they can be malleable because depending on it, right, like you can shift the friends around and they don't really care. So that's why it's a sometimes situation.
It's like two friends.
Another one, yeah, Trevor.
Isn't that it's sometimes soluble?
Yep, same situation. So sometimes they're soluble, which also means sometimes they are aqueous conductivity. And what we'll hopefully identify in this unit is why the covalents have so many sometimes. It's all about, there's more forces going on here, because there's 5 different types of friendship forces that can exist.
Oh my gosh, it's like friendship power.
And so depending on what type of friendship force it has, changes the properties it exhibits, right? Because the tighter the forces, we know probably the less malleable it is. If the forces are fairly weak, it's probably fairly malleable, right? So
radiative van der Waals forces.
so that is one of our type of forces. Yeah. Okay, now this is the other type of covalence that can exist. Okay, majority of covalents are covalent molecules. But we also have these things known as covalent networks, which are really cool. Once again, they are the rare exception, so don't assume something is a network, because most likely it's not. But what a covalent network is it's still a shared relationship, but it's a massive, large network of shared relationships. So these types of things you would not be drawing yourself. None of the ones you've done are considered networks, because they are massive bonding 3D things. So 2 examples of a network. One is graphite. So this first picture up here is the molecular view of what graphite looks like. Okay, so everyone take your pencil for me. Hold your pencil. Mine's not pencil. Pretend it's pencil. If you don't have a pencil, look at your friends.
It does.
And I want you to look at it really close. Look at your pencil, the lead, the graphite.
My eyes hurt.
I know, some of you have your pencils upside down. Flip it around. Okay, now, this is so cool. Like, I don't think you appreciate every time you use your pencil how cool this is. Okay? So graphite is a network of carbons in these hexagonal patterns, but connected to each other. So a lot of hexagons all connected. Okay? In your pencil, okay, the pencil lead, we call it lead, it's graphite, right? Are sheets of graphite. So what happens is when you take your pencil and you write on your paper, you're literally laying those sheets of graphite down.
Boy.
Isn't that cool? You guys do not look as impressed as you should be.
Wait, can I do that with air?
I'm sure, yeah.
In the levels,
Wow. I have sheets of graphite in my
Ooh, so Aiden brings up a wonderful question he's going to answer for us. Okay, close your mouths for a second, everybody. So Aiden asked, then what does the eraser do? So what do you think the eraser does when you rub it on there?
It sticks to the
It
graphite.
picks up the pieces of. It just makes it invisible.
Yep, it just pulls them off because they're not like bonded to the paper. It's just another friendship force, right? But the eraser just breaks the friendship force and pulls them off. And that's why when you erase, you end up with a bunch of little black graphite everywhere, right? So the cool thing is a single layer of graphite is extremely strong because of that network that's going on. but the force between the sheets is just a friendship force. It's an intermolecular force. Now what's really cool, so stare at your pencil again. You can go cross-eyed, look at your pencil. Okay? At the molecular level, what is in your pencil is the exact same thing as a diamond.
I'm insane.
Whoa.
Okay? It's crazy, right? So the chemical formula for graphite is C. It's just carbon. The chemical formula for a diamond is C. It's just carbon.
C4.
But structure determines function. Diamond is bonded in a hexagonal pattern, but not those sheets. You can't quite see from the picture, but the sheets are directly bonded to each other. So it's a massive bonding going on in 3 dimensions in all sorts of patterns. Yeah, Alex.
So if we are made of carbon, can we technically be turned into a diamond?
Yeah, there's, what's it called when you get turned into ashes? Yeah, there's cremation places where you can take your ashes and they'll turn you into a diamond.
Oh my gosh.
And then what, they like make it into a ring, and then your kids can wear that ring, and they're gonna if you got turned into a diamond, then you have so much going on. That's so weird though. Like, hey, this is my mom, okay? Take it easy, and like yeah, but then it's like a little dead person on your hand.
My brother was like, if Sam's that, I'm having a hot person.
Okay, you can all plan out what type of diamond you're going to be turned into.
This is my mother's wedding ring. Oh, you mean it's your mother's wedding ring? No, it's my mother's wedding ring.
Okay, here's what I want to do now, okay? So I want you to think, and I don't want you to say these out loud. You're going to answer giving thumbs up or thumbs down. Okay, so answer to yourself. We're going to go through the properties of covalent network, and I want you to think, okay, if that's its structure, what makes sense about its function? So the first one I want you to answer, so don't say it out loud, just give me thumbs up or thumbs down for melting point. Okay? So do you think, don't say it out loud. So give me a thumbs up for high, thumbs down for low. Knowing what you know about the structure of covalent networks, what would you predict their melting points to be like? Show me with your vote. Keep it like underneath your chin. So thumbs up, thumbs down for high or low. You don't get a smiley if you don't try. They're both types of covalent networks. Yep. All right, if you're saying high, you can have a smile. Right? Because if you think about it, like it's going to be really hard to break all those bonds going on. Right?
Can't you like evaporate a diamond? Like where you,
In theory.
like you put it high enough. Well, basically what, like, I'm pretty sure when people like evaporate diamond, because carbon doesn't really turn to a liquid, what they, like normally what they do is they
just make it sublime. Some of these are straight from the solid to gas.
well, yeah, basically, where they just burn it and I think it
Whoa.
burns. It's like a really experimental way to burn.
Thank you.
No, I've never researched burning diamonds. I'm going to have to now, though. Well, that's- Yeah.
I'm having way too much fun with this.
Where's my
So
water?
this is the all that massive quantity, and this is like obviously it's much bigger that way. But then there's diamond. There's bonds actually between like that bond to that, so that's like.
Dude, can
So the force between is not a true bond. It's not a bond. But the bond between are that's what makes diamond like so strong.
I mean,
And I was like, and then I actually just changed the name, so they
I mean, sort of, but no.
hashtag doubt no.
Okay, next one, everybody. Give me a thumbs up or thumbs down. Would you predict that covalent networks, once again, there's always exceptions, but in general, Would you predict covalent networks to be malleable? Give me a thumbs up or thumbs down. Malleable. Are covalent networks malleable? Thumbs up or thumbs down?
No. Because didn't they say you can't like cut the diamond?
Yeah.
Yeah.
Yeah, so they're not malleable.
You know how people they break things with diamonds?
Smiley? She didn't say it.
Yeah, so it's just like they're going to be very resistant, right, to any shift, but those bonds can't be maintained. So, okay. Now, what we're going to do, everybody, is now we're going to, so the box we're focusing on now, so those are the example of the 4 different types of solids that exist. Okay, so things can be ionic, metallic, a covalent molecular, or a covalent network. Once again, those 2 are both covalent. Yep, so those are the 4 types of solids that exist on planet Earth.
Whoa.
Okay, now we know it, I guess.
I guess this, because later it gets more complex, or
Oh, that's it. That's really that. Now, what we're going to do, though, is dive deeper into this one of the molecular covalence and look more at that force between our intermolecular forces. Okay? Allison, what have you seen?
Hashtag delicious.
It's so it's a 4th state of matter. So no, the 4 would say the 4
Plasma
types of
is
salts.
just
So plasma is not.
molecules.
Okay, with intermolecular forces, everybody.
Right.
Okay. Today we're going to learn about 3 types of intermolecular forces that can exist within molecules. Now, once again, if you want to make a note to yourself at the top of this, these apply only to covalent molecules. If something is ionic, it doesn't experience this force because it has the ionic force. If something is metallic, it doesn't experience this force because it has the metallic force. But covalents, because they bond in small things, can then experience these friendship forces between the molecules. And networks can somewhat too, like the graphite does. So anything covalent can have it. Yeah, good connection again. Now, this is our key word once again. You haven't noticed this is a favorite word of chemistry because everything can be explained by positive and negative forces. Okay? So what we're going to be looking at today is a Coulombic force, which describes something that is positive and something that is negative and the force they feel between them. Now, we've talked about it before. Coulombic forces are influenced by 2 factors. What are the 2 factors that influence a Coulombic force?
distance.
Yes, distance and magnitude.
Oh yeah.
Oh yeah.
Oh yeah.
Oh yeah.
Oh yeah.
Okay, because Coulombic forces are a vector, right? So that's what we need to think about as we think about why this is a stronger force than that one.
Ashton.
It's going to go
Haven't
back to
seen you
one
in
of
a
those
while.
2 reasons every time.
I've always seen
Okay.
that hoodie though.
The more everybody you can centralize into this one theme, the simpler it all becomes. Because it really is, it's always just about positive and negative things, their distance and their magnitude. So the first type of friendship force we have is known as a dipole to dipole force. I abbreviate it as DE. If like on your homework and stuff, you can write it that way. Okay, this force is the force that is experienced when the positive end of a one polar molecule, okay, key word is these things are polar, is attracted to the negative end of another polar molecule. So with our little water molecule friends on your desk, this can be described as a dipole to dipole force, because we know that water is polar, the hydrogen end of the water is positive, the oxygen end is negative, and positive and negatives attract. Right? This is why if you try to put the 2 hydrogens together,
It works.
They-
You have to pull them off and then you put them on the back.
no, don't break my waters. Okay? And same thing like the oxygens, right? Don't connect. So a dipole-dipole force is when you have one polar and another polar, and so they link up. Okay? Dipole to
The
dipole.
water's sticky.
Now, as we talk about magnitude and distance, okay, the magnitude of polar molecules is measured through their dipole moment. Okay, so this is not something you have to know how to calculate, but it could be given to you. This number indicates how strong of a shift of the electrons there is. If you think of our electro maps, like the red and blue pictures we colored last unit, Something with a really high dipole moment would be very red and very blue. Something with low dipole moment is mostly like grayish. Okay? So the trend I want you to notice here is that as dipole moment increases, right, so as this goes up, we see that the boiling point also goes up. Once again, structure determines function. If the molecules are held tighter together, it's going to be harder to pull them apart. So the higher the boiling point, the stronger the dipole force that's going on, and vice versa. So given one of these numbers, you should be able to make a claim about the other, because it's a direct relationship every time. Exactly, yeah, if something has a high boiling point, you have to say, okay, the forces in that must be pretty strong, right? Okay, second type of friendship force is known as a London dispersion force. It's also known as your van der Waals forces. I don't know why it has so many names, but the most common name now is a dispersion force. Yeah. Normally, I guess it's because like multiple scientists maybe discover it at once or something. They have different names. But anyway, so, okay. So first friendship force is a dipole force. Second one that's possible is called a London dispersion, or you can just call it dispersion force. Now this force, in connecting it to a dipole force, is a temporary dipole. Okay, in a permanent dipole, the electrons are one way, and so you get negative and positive. If we were a polar molecule and you guys are the electrons, you would all be on this side of the room. Okay? But if we're not a polar molecule, electrons are mobile still, because they always are. There's nothing pulling you one way or the other. But if you're always in motion, so let's imagine, we're not going to do it because this would be a little crazy, but we're all stand up and just start running around the room. Oh. And then I said, stop. Is there a chance that at that moment, more of you could be here than there? Yeah. So in that moment, this side of the molecule would be more negative, and this side of the molecule would be more positive. It's a momentary dipole. Now, is it strong? No. Because electrons don't truly ever freeze, so that momentary negative and positive can easily be broken. So this is the type of force that something that is nonpolar experiences. It's how you explain how everything can eventually become a liquid. Because there has to be a force if it's going to become a liquid, right? If there's no force present, it would never become a liquid. But it's not very strong. Now there is kind of a bumper car effect a little bit. So imagine like if we're electrons, and the class on the other side of that wall are also electrons. If we all run towards the wall, what's going to happen to them? Right, we'd all like push them because they're like negative. So you can they can kind of influence each other's momentary dipole, but there's nothing holding the electrons there, so it can be broken very easily. Okay? So we look at some data here. Oh, but it's all about the more electrons you have, the stronger this force can become. Which makes sense, right? If you have like 80 electrons to shift, you're going to get more of a negative than something that only has 2, like helium. So this is why to get helium to become a liquid, you have to cool something down to 4 Kelvin. Helium won't become a liquid until you get to 4 Kelvin. And as of right now, scientists have not made it ever become a solid. So that's helium, bad friend.
Wait, so if you drink helium, would your voice become higher?
Oh yeah, there was like this thing where like these people infused helium into beer, so they were drunk but talking in high voices. It was really funny.
If you tried to drink actually liquid helium, you would freeze your face. That'd be like trying to drink liquid nitrogen, but 10 times liquid. I don't think it would get to your vocal cords for you to have time to
Because it has very few electrons, and so there's very, very little force pulling it together, and so you have to get it really cold.
Yeah, as of right now, scientists have not found a way to get it cold enough to force them to come here.
Oh, so it's a gas, right?
Yeah, so it's a gas. Because its attraction to itself does a lot of self-taking.
Yeah, it's really interesting in that, and just yeah, it kind of goes against what we want. Yeah.
And
I
so
heard that like with helium and stuff.
you have to get it really cold, and so that there's not a lot of kinetic energy. And then once you get that low enough,
The
then
pressure
you
of
get it.
25 atmospheres, as well as like absolute zero.
To get it to be there.
Yeah, but since like the way that people make absolute zero a lot of the time is with vacuum.
Then you can't apply that immense amount of pressure.
Yeah.
That is interesting. So what we see here, everybody, look at this data, okay? So for the noble gases, okay, xenon, you can turn into a liquid at 100, if you go below 166. Because it's much heavier. So it has a much stronger dispersion force than helium does. Now, the official word, I passed it, but I want you to star it. Okay, the word that describes this ability to shift electrons is known as the polarizability. Okay, an atom that is very polarizable has a lot of electrons that can shift. I once read it actually in one of my college textbooks, and my favorite definition of polarizability is they described it as the squashiness of the electron cloud. Like that's literally what my college textbook said. Because if you think of as the electrons move, it's squashing the electrons one way more than the other, and so you get that like momentary shift in electrons. Okay?
Bacon wiggles.
I know.
The
I was
bigger
like,
it is, the
I was
more
like,
it can wiggle.
is even a word? Can you use that? Okay, so last type of friendship force. So we have dipole in the middle. Dispersion is the weak force, right? Not very good friends. Those are just like your passerby friends, like, hey, how you doing? But you're not like great friends with them, right? Dipole are good solid friends, but hydrogen bonds, those are your best friends. Okay, this is an extreme dipole force, so it's stronger for two reasons. Okay, I'll give you a second to fill those in.
From the Lord of the Rings, a hydrogen bomb.
Okay, come to this picture on your notes, and I want you to draw some images with me. Okay, I won't go to the next screen if you're not done filling in blanks. Okay, so in a water molecule, we talked about that oxygen has a higher electronegativity than hydrogen, so it's going to pull the electrons towards itself. Okay, causing this side to be negative and this side to be positive. But two things cause it to be an extreme dipole shift. One is that NO and F are very electronegative. They're very, very strong in the tug of war. Okay, so this pole, I'm going to emphasize by thinking my arrow. Okay, that one is really good at pulling. The second factor is hydrogen has how many electrons?
One.
One. So if you pull the only electron it has away from it, what's left?
A proton.
Just a proton. So you get an extreme positive on the end because that's all that's left. And so that increases this friendship force. So the hydrogen bond forms from one water molecule to another water molecule between them. Okay? Make sure you note that this is not the hydrogen bond. They use the word bond, which I almost don't love because it's not a real bond. It's just a friendship force, but it's so strong that they put the word bond on it. But questions on that? Joel?
Isn't that why hydrochloric acid and hydrofluoric acid are so like solute, well, so like acidic because the hydrogen has like absolutely nothing. So like
It's part of it, yeah. Yeah, because when we get into our acid and base unit, it's all about the ability to give up that hydrogen. And so if that hydrogen has already been lost its electron, then it's like, well, I'm just going to leave anyways. So yeah, it has definitely linked to it.
has nothing left to lose.
Yeah. Alex?
Are we allowed to use the word friendship force on the
So no, use intermolecular force. I know I come up with these analogies because hopefully they help stick.
Can we use it on our test or like
Just
not on
like
the
I don't use it on ours because we want to
Just
practice
like
like
the bond
routine.
stick.
I've got.
Idea stick.
Thank you for asking
Just
that,
like
Alex.
the IMF stick.
With this
What
force,
if you did like a small definition, you did like,
Oh, yeah,
the
you just-
friendship forces, in parentheses IMF, and then you just keep on using friendship forces.
I bet that would be
Maybe
fine.
make a key or something.
You just give them like a decode system.
So the ghosts are actually friends.
I want you guys, is this picture, do you guys have this on your notes? Did I get that show up?
Yes.
Sometimes you just don't. I want you to know, so all of these red dots, so circle them on your paper to emphasize it. These are all different examples of a type of hydrogen bond. Okay? So to create a hydrogen bond, you have to have a NOF sandwich. N-O or F sandwiching an H. Okay, so notice here's your H. You have an N on this side and an N on that side. It has to be sandwiched. Okay? Same thing here, you have an N on that side and O on that side, that's still fine. Okay, but if it's not sandwiched between, you can be deceived at what you might think a hydrogen bond could form. Okay? Make sure you have it between N, O, or F. Okay? Now, hydrogen bond is the strongest of our three forces because it's an extreme dipole of it. If you don't believe in the strength of a hydrogen bond, then go and belly flop into a swimming pool and you'll feel it. That's why it hurts, is because the water molecules are playing Red Rover against you and you lost.
That's not true. I won. I got
We did break through.
I mean, I guess it depends. It's like you get hang wired in Red Rover and say, no, it was worth it. So I guess that's up to your turkey.
Yeah,
I don't count that.
I got through.
You did get through.
I did get
With
through.
a bit of resistance.
It hurt. They were strong. I was just
That's
stronger.
true. That's true.
Gravity wins out.
Well, then why is it that slow, like, why is it that going slowly doesn't work? Polar? Like,
Closer.
do you think that, like, well, the way, I don't know what I'm trying to, like, ask. Like, the question I'm trying to ask is, if you were to hit the water really fast, it hurts, but if you hit it really slow, it doesn't hurt.
Because because they're all structured, right? There's like kind of a structure. We'll learn more about it next time with surface tension, right? But if you go in slow, you can break the surface tension before you feel the
So is
tension.
that kind of like
If you go fast, you just hit the tension and then it breaks.
is that kind of like Newton's law of an
What it
object
does,
in motion will stay motion till
Oh, sorry.
or not, like it wants to stay how it is.
Kinda, yeah, it definitely could be linked to that, Trevor, for sure. It's kind of cool to think about. I know Aiden up here is a swimmer. I don't know if anyone else, I mean, somebody probably like to swim. But like literally swimming is so cool if you think about it, is literally you're grabbing a bunch of these with your hand and pushing them back, and that's what propels you forward.
Whoa.
Like that's how swimming works, right?
I'm a waterbender.
It's just
So
like
if we could do
finding-
that with air, we could fly.
There's
Like
actually,
if I could grab air particles and push them down, I'd go up.
you actually,
So if air is water,
I just started flying.
there's planets that actually
wait,
allow
that's
you
not how that works.
like you need to have like oxygen mask and stuff to like be able to breathe and not die.
Right.
But if you just have like fly like
So
a
dense.
yeah.
The air's so dense.
Why do they have weather?
Okay, did everyone get this? Is kind of just a summary table of everything. Did everyone get it filled in?
No, wait, no.
Yes. Yes, so we'll talk all about those applications next time. Yeah.
What is the word under N? The first word.
The stronger when the molecules are closer. Because it's all about distance, right? So. I know, I hate when they land rather than far. Okay,
How on
everybody
earth did a
good?
guy in 1908 create liquid hydrogen? How on earth?
Somebody have one that we can borrow? Yes!
Wait, can you go back and you have the pictures?
Dude! It's like 3 meters. That's cool.
So it's really cool, you get a bunch of these and then you can see that's why snowflakes make such cool shapes. It's because the snowflakes can bond, right, and all sorts of bond, hydrogen bond.
Wait, guys.
Pass it around, pass it around.
Okay, now I want you guys to notice something because this is your paper too.
Yeah, it's cool.
Too cool. Everyone knows.
Grow. Make it grow.
Oh, yes, add.
Make it grow.
Add on.
Okay,
Add
give me
your
your
water.
chance, everybody.
Add your water.
I want to get to our example problem before the bell rings so you can see what your homework's going to be like. Okay? So what I want you to point out notice on here though, so this shows the strength of force between all the different things we've talked about today. First note, pay attention that the scale is not to scale, right? This is 0 to 2. This is 100 to 400. Okay, so the distance, don't think it like means the same. It changes drastically as we go this way. So notice that our intermolecular forces all are weaker than an actual covalent bond or an actual ionic bond. right? To pull this apart, the hydrogen and the oxygen, takes a lot of force. But to pull two water molecules apart, in comparison, doesn't take much. Now, hydrogen bond is classified as the strongest, then dipole, then dispersion, but I want you to notice this section. There are times when a dispersion force can actually be stronger than a dipole force in another. And we know the AP people will love to throw out exceptions. So every year they love to bring this up. Now, the catch is you don't have to memorize it. But given data, you should be able to match it. Meaning, if you're given a molecule that has dispersion forces and a molecule that has dipole forces, but molecule A has a higher boiling point than molecule B, that must mean that the dispersion forces in A are outweighing the polar forces in B. And we'll see this more as we go. But just recognize that there is some overlap where if you have a molecule that's really big and has lots of polarizability versus something that is like barely polar, right? It can actually be stronger than the other, okay? All right, your main homework assignment tonight, homework 3.3, looks kind of like this table, where I'm going to give you a substance and you have to identify what forces are present within it, okay? So the first thing you're going to want to do, because it will narrow down your choices, is identify what bond is in this molecule. Okay, so NH3, is it ionic, covalent, or metallic?
Is Gorda thing is like okay, but
Okay, how do we know to remind us? See some of you looking at the periodic table, which is where we look.
Because it's non-metals.
So non-metals with non-metals are covalent. So you look at that staircase. If they're both on that side of the staircase, it's going to be covalent. Okay?
What?
If it's one of each, then it's ionic. So
What if it's like in the middle kind of thing?
What do you mean by middle?
Like rubidium or something.
So those are all metals still.
Really? Okay.
So this is your dividing line. So these are non-metals. Everything else except hydrogen
Okay.
is a metal.
So then like water would be something.
You got it.
Covalent?
Yep.
Gotcha.
Oxygen's a non-metal, hydrogen's
Yeah.
a non-metal. So, yeah. Okay, questions on remembering that from last unit? Okay, so then your next step, everybody, give me your attention here. If it's covalent, you then are going to want to draw a Lewis structure. The reason why it says if applicable is if it's ionic or metallic, you don't draw Lewis structures for those things because they have different structures. So you just put Na to the next name, okay? But this one we need a Lewis structure for, so let's draw it out. Okay, I'm going to kind of draw them fast, but if you need to review Lewis structures, come see me and we can definitely review it. Okay, but that's what it's going to look like. Okay? Now, if it's covalent, then it's going to be these options only. Okay, because once again, that's for ionic and metallic things. Okay? So, how do we know if a molecule exhibits London forces?
If it exists.
If it exists and it's covalent. Yep. Because anything that's covalent has electrons, and anything that has electrons can be polarized, so it can experience London forces.
Only covalent, London forces, or an ionic and metallic be?
No. Yeah, great point, Jess. So if it's ionic or metallic, it wouldn't have London. So only covalent. But everything that's covalent can have. Yeah. Okay. How do we know if something has dipole forces? So the question is polar or not. Okay? So is this molecule polar? Yes. So yes. If it was no, then it would be no.
That's
Well, why does it say Lewis structure if applicable? Like, do ionic bonds not able to Lewis structure?
No, because they don't share.
Oh,
They're just that positive,
So
negative.
then
You just don't
every Lewis structure we've been doing was covalent?
Ding, ding, ding.
No.
Yeah.
Oh.
Okay. How do I know if it has hydrogen bonding? You gotta look for Knopf sandwich.
And there's
Knopf
not
sandwich.
that.
Okay, so you need N or F
There's no
with
Knopf sandwich.
an H.
There is a.
Your mom's a Knopf
So
sandwich.
N is connected to H.
That doesn't make sense.
You have multiple. You're not gonna have a single thing of NH3. You're gonna have a ton of NH3 molecules. It is a sandwich because you're gonna have another NH3,
Oh,
and it's gonna be
great
right
point.
here.
With how I have it drawn, why do I not have a sandwich?
You see? You're gonna have a second.
Remember, yeah, it's the
And then
friendship force.
It's
So we're talking about this with another one.
one hurt did I rip my paper by grabbing it. Just like picked it up.
I switched out of AP World.
How did you do krypton?
Is that so? Yeah, you don't see the sandwich if you only draw one. But the biggest thing with the sandwich is make sure it's connected to the H, right? So yeah, great point though. Okay, questions so far? Okay, let's do two more before the bell rings, okay?
Is that as far as we have to
Okay,
go?
krypton is our next one. It doesn't really bond with anything, so its Lewis structure is just itself.
Type of bond. Ooh, not existent.
Okay, now we're gonna call it covalent because it's non-metal, right? And it'd be, because we're looking at a krypton interacting with another krypton, right? Now once again, they don't technically bond, but they're both non-metals. I'm gonna draw two just to show. So what we're looking at is what force is felt between them. So does it have dispersion forces?
Yes.
Yes.
Does it have
They're
dipole
also called
forces?
dispersion.
No.
No.
And definitely not hydrogen bonding, so that's it.
How would you know if it's a network?
Sucks.
So we don't have to do the last three? We do, we're just not gonna do the last.
Just, they haven't been applicable yet.
Oh.
So, Sophia. So it's because it's a momentary shift in electrons, but like ionics, the electrons permanently are one way and the other. And in a metallic, they're kind of just always everywhere. So does that make sense? Yeah, good question. Okay, I'm gonna go to this so we can skip down real quick.
Wait, no.
Okay, look at this one here, everybody. All right, KMNO4. K is a metal. These are both non-metals. So that would make the bond between the whole thing,
Ionic.
which means that's not applicable, which means I just checked the ionic box and I'm done.
Oh.
So if something is ionic, it's just ionic box. Okay, last question is the covalent network. Pretty much don't assume anything is a covalent network, except for diamond, graphite, and silicon dioxide.
Oh, good.
So,
Thanks.
right.
So what is silicon dioxide?
Glass.
Oh, yeah, that's definitely a covalent.
Yeah. Not kind of, but not really, because it's like lots and lots and lots and lots of bonding. So you don't have to, if it's a network, you don't have to draw it.
So if it just has this C on it,
Okay. Come see me though if you have questions on, the biggest thing is, so next time we will have a little quiz similar to this table where I give you some structure and you gotta tell me what forces they have, okay? But the homework should hopefully give you lots of practice with that. Oh, I need your water, please.
Harry Fromm, come to the front office, please. Harry Fromm.
I think.
I'll just steal yours and put them back.
Don't have dipole diagrams. But yes, they would have all right, then if you could hand me your water as you go out the door, or if you left it on the table.
SiO2 has a covalent network. Why? Why does it do this?
You're good at timing.
Probably stop the thing.
Oh yeah. Stop. Stop.
Wait, where's the camera? Peace out, home slices.